Welcome back, everyone, to the wonderful world of 12.2. Again, in this section, we're talking about vectors, right? And so we did kind of the introduction last time. We talked about what are vectors, position vectors, length of vectors, things like this. And in this video, we're going to extend on that or expand on this, and we're going to talk about vector addition and scalar multiplication. So, right, what are some more things that we can do with these new toys that are vectors? We're also going to talk a little bit about some properties, right, of these vector addition and scalar multiplication. And then finally, we're going to talk about, a few types of problems that can be asked, regarding these vector addition and scalar multiplication. So, all right, that's enough of that. Let's get to it. So again, we have this new toy, this new thing, this vector. Oops, already I'm having a little bit of a technical thing here. There we go. Pen's away, good. I'm right here. All right, so yes, we have this new toy, this new mathematical object vector, and we want to know how can they interact with each other, and also not only other vectors, but also real numbers. So these things are going to be called scalars, and you will see why here in just a minute. So let's go ahead and define these things first. So we have a few vectors here. We have our vector A, we have our vector B, right? And they have components. We're going to talk about three-dimensional vectors right now, but these should also work with two-dimensional things, right? So if you only have two components. But we have three components. We have A1, A2, A3, B1, B2, B3, right? And then finally, we're going to have C be some real number, which again, we're calling this a scalar, kind of moving forward to kind of differentiate between vectors and then just regular old numbers. We'll now call them scalars. So the first thing is vector addition, right? How can we add these two things together? And if you were probably just guessing, it behaves exactly how you would guess. And that is, we're going to go ahead and add each piece. So for instance, we take the first piece of each one of these, right? And if I want to add vectors A and B together, well, then we just add the first pieces together. So A1 plus B1. That's what's going to go in our first slot, our first component. For our second component, we're going to, add the second components for A and for B. So we're going to take A2 plus B2. And then finally, in our third components, we're going to take A3 plus B3. Again, just kind of adding each component together. And that will be a good definition, and we'll see that there's a good reason why this works out so nice. And then, second, scalar multiplication. So if you have a scalar, suppose that this is 5 or 2 or negative 20 or whatever you want, right? And you want to multiply that by a vector, right? So your favorite vector here, A, suppose. And again, just kind of if you were guessing, you'd probably guess, well, let's go ahead and distribute it to each piece, right? So we're going to take C times A1. And again, this is multiplication here, C times A2, and C times A3. So you just kind of distribute it to each piece, and this turns out to be a really useful definition. So this is what we're going to be using for scalar multiplication. And again, I mentioned it at the beginning of all of this, but this was for three-dimensional vectors, right? Things with three components, A1, A2, A3, B1, B2, B3. But you could do the same thing essentially for two-dimensional vectors, or right, really any dimension you want. If you had some system, you had four dimensionals or five dimensionals, right? You could use the same sort of idea to define vector addition and scalar multiplication. Okay, and I told you, right, that these end up being really nice definitions, and one way to see how nice they are is to look at, what do they actually represent geometrically, right? So we've defined some algebraic thing, how to add together vectors, how to do scalar multiplication, but it turns out this ends up being very useful. So let me go ahead and kind of show you what this looks like. If you have a vector A here, and you have a vector B. And first of all, maybe I could draw B, maybe initially it's out there, but remember vectors are considered equal so long as they have the same magnitude and direction. So actually this B, let me go ahead, and it turns out to be very nice if I just pick this up, and I would like them to both have the same kind of initial starting point right here. Probably this, would be the origin. We'll make these position vectors and everything. So we have vector A and vector B. And just kind of as an FYI, quite often, when I type these things, I use these bolded A and B, right, to denote that these are vectors, and you can see that this C right here is not bolded. so scalars would not be bolded. When I'm writing these by hand, it's really hard to bold these things. Even if I press down hard with my pencil or pen or whatnot, it still doesn't come out so well. So I use the little arrow over these things just to remind ourselves that these are vectors. And I'll try to stay good about writing this little arrow over anything that is a vector, just so we can, clearly differentiate between vectors and scalars. Sometimes I do forget, and I apologize, and please, do ask either in the comments or in class or something like this if I forget. Okay, so here is our vector A and our vector B, and the claim is that if you wanted to know what does A plus B look like, right? So if I was to go ahead and do this vector addition, essentially what it looks like is if you were to travel along one of these vectors, so let's first travel along A, and then we were to travel along B. So I'm going to get myself an extra copy of B, right? Again, so you can kind of think about me picking this up and moving it, but I actually just want another copy here. So if I want A plus B, it's that I travel along A, so it's like I travel along A, and then I travel along B, and wherever I end there, this right here is A plus B. So this is the vector, and let me go ahead and maybe just squeeze it in right here, A plus B. So this is the vector A plus B. This is our vector addition. And you can also see that this works out very nice, right? One thing that we really want is that addition, right? It shouldn't really matter the order in which you add things together, right? So A plus B should be the same thing as B plus A. So if I was to travel first along B, here, and then travel along A. So I'm going to use another copy of A just right up here. So here's another copy of A. So if I travel along B first and then A, so that is B plus A, notice I end at the same spot. So this vector right here, A plus B, is the same thing as the vector B plus A. So sometimes you can see now that we've drawn these extra copies of A and B, you kind of see like a little parallelogram, right? So sometimes I've heard, in other videos or other textbooks and things like this, right, that the vector addition A plus B is kind of the diagonal of the parallelogram generated by vectors A and B. So we can kind of see we have some nice parallelogram generated by vectors A and B, and then this A plus B is one of the diagonals here. All right, so that right there is the vector addition. Scalar multiplication, again, has a nice geometric kind of feel to it. So if I had a vector A right here, and if I asked you, to kind of guess, what do you suppose 2A looks like, right? So 2A, so that we're multiplying by the scalar 2. Well, the claim is, well, it should look like A, but maybe twice as big to some extent, right? So it's going in the same direction as A, but, right, it's scaled up by a factor of 2, right? It's twice as long, right? Maybe there's the halfway point or so. It's twice as long as the original A. So there would be 2A. And so that's why we call these scalars, because they literally do scale up. It's like as if you were to take this, maybe I highlight here or whatnot, and I actually scale it up by a factor of 2, right? It's going in the same direction and all that, right? It's just scaled up by a factor of 2. Now, likewise, we can actually scale in the negative direction, right? So if I asked you, what do you think negative A looks like? Or this is really negative 1 times A. So this is actually going to be the same length as A, but it's heading in the opposite direction. So now this scalar multiplication, this thing that we've defined up here, literally scales vectors. It scales them up or scales them down. You can even scale them in this opposite direction here, right? But it's literally scaling vectors, and that's why we call these things scalars. All right, so we've been talking a lot about theory here, right, with these definitions and kind of these abstract ideas. Let's actually put some concrete numbers to this, right? So here's an example. I have vectors A and B, and notice I'm going to be drawing these things eventually, so I think it's very nice to maybe start off in just 2 dimensions. And then we'll go ahead and first of all, we'd like to evaluate a few things, and then we're going to go ahead and sketch. So the first thing is that I'd like to evaluate A plus B. So let's go ahead and write this down. A is 1, 3. B is negative 3, 2. And if I wanted to add these vectors together, again, based on our definition, we would just add each piece, each component together. So I'm going to go ahead, I'll show probably more work than you would show, on a quiz or an exam or something like this, but I'm going to go ahead and do 1 minus 3 for our first component. and then 3 plus 2, again, just adding those second pieces together. And now I'll take a line to simplify here. So negative 2, comma, 5. So this is our new vector. A plus B would be negative 2, 5. And like I said, this is probably more than I would show on a quiz or exam or once I've had some practice, right? Eventually we'll get quite good at just looking at, 1 plus negative 3, that's negative 2. 3 plus 2, that's 5. Oops, that one didn't highlight for whatever reason. All right, and so I would just probably write down negative 2, 5 and call it good. All right, let's make this a little bit more complicated. Not only do I have some vector addition going on, but I'm also doing some of the scalar multiplication that we were talking about. So let's go ahead and do that. So negative 3 times A, 1, 3. Again, that's what A is up here. Plus 2B, so that's negative 3, comma 2. And we're going to go ahead and maybe first I'll go ahead and take care of the scalar multiplication, right? Still using this kind of PEMDAS sort of thing that we know from our good old algebra days, or really arithmetic days. So why don't we go ahead and do our scalar multiplication. And again, scalar multiplication, it distributes to each piece, just kind of, what you would guess more or less. So I'm going to do negative 3, comma, negative 9. And then again, I'm going to distribute this 2 to each piece here. And this isn't really distributing. Probably mathematicians would yell at me. Again, it's not true distribution, but it's kind of like it, right? So, and then we've simplified down. We have all of our scalar multiplication done. Now let's go ahead and do our vector addition. So maybe I'll do this one the fast way, right? So negative 3 plus negative 6, that's going to be negative 9. And then negative 9 plus 4, that's going to be negative 5. So this right here would be my final answer. Should probably get in a better habit of maybe like highlighting these things or whatnot. So these are my final answers here. All right, and then so this is kind of the root algebra of it to some extent. And then if we wanted to go ahead and maybe do the geometry as well and really see that these things do behave like I've told you they do, let's go ahead and sketch these. So I'm going to sketch A and B, and then we'll go ahead and do the more complicated things, the A plus B and the A minus B. So A and B. So A is 1, 3. So, okay, 1 in the X direction and 3 in the Y direction. And let me go ahead, I'll use blue for this. So that right there is going to be A. All right, B. B is going to be, let's see, negative 3, 2. So 1, 2, 3 in the negative direction, 1, 2 in the Y direction. Maybe I'll go ahead and use green here. And so this is B. And kind of if things are behaving as I would expect, I'm expecting A plus B to be somewhere around in here. So I'm thinking somewhere around in there, that should be where A plus B is. Again, if I was to travel along B and then A, or A and then B, right, somewhere along in there. But let's verify, right? Now that we have the algebra and everything, let's verify this. So let's first compute A plus B. In fact, we've already done that up there. And now let's go negative 2, 5. So negative 2, and then up 5. 1, 2, 3, 4, 5. That ends up being, pretty darn close right here. Negative 2, 5. For that one, maybe I'll use red. Kind of running out of colors here. So this is going to be A plus B. And then finally, why don't we just guess where we think A minus B would be? Right, so I need to travel along A, and then I need to travel along B in the opposite direction. So really negative B would be something like this. So here's negative B. And then if I wanted to go along A and then go along negative B, oops, didn't really highlight enough there, I would need to do something along like this, right? So the place that I would end would be maybe down here somewhere. All right, so let me kind of delete that and see if that's close at all, right? So let's go ahead and compute. We haven't done A minus B, so let's do that really quick. 1, 3, and then I'm going to subtract away negative 3, 2. So, okay, 1 minus negative 3, so that's going to be 4. And then 3 minus 2, that's going to be 1. So 4, 1. So, okay, 1, 2, 3, 4, and up 1. Hey, that's not bad. This one I'll just use black. Oops. So this right here would be A minus B. So that is, you go along A and then you go along B in that negative direction. All right. So that is quite a bit of exposure to the vector addition and scalar multiplication. Now I'd like to go ahead and give you a nice theorem, and I'll talk over this proof, right? I've already went ahead and laid out what the proof looks like. And basically the question is, if you scale A by a factor of, let's say, 2, or something like that, or 3, or 5, or 100, the question is, well, how long is it? Right? How long is that new vector? What is the magnitude? Remember, magnitude's talking about length. What is the length of that new scaled up vector? And again, kind of looking at the geometry, what we've been thinking about this, you'd probably say, well, it's just going to be however much you scaled it by times the magnitude of the original vector. Right? So likewise, back here we saw, right, if you have vector A, again, maybe this has length 5 altogether. And if you scale it up by a factor of 2, then it's going to have length 10, right? So it's going to be 2 times 5. Or if you go in this opposite direction, right? Going in this opposite direction, really, it doesn't really change the length so much. So we go back here, and so this is pretty much correct, except for we're off by a little bit, right? The length of a vector shouldn't be negative. And if you scale in this opposite direction here, problem is the scalar right here could be negative. And so really this should be the absolute value, right? Think about if we were to go ahead and plug in a -1 here, right? If you plug in a -1, right, scaling, flipping it and going in this opposite direction doesn't change the length, right? So when you take the absolute value of -1, that would become +1. So, okay, this seems to be working out a lot better. And you can see this is a little bit confusing, right? So we have an absolute value, and then we also have a length of a vector, right? And these are two really different things, fundamentally different things. Here, there are connections certainly and whatnot, right? But the computations, everything that you're doing for an absolute value versus a vector's length, they look very different. Remember when we were talking about the length in the first video, right? We said that there's actually two different denotations for this. You can also use these double bars right here. And this becomes very useful where you have equations that deal with absolute values and that deal with magnitudes of vectors. So I would probably write it like this. So again, if you're interested in what is the length of some scaled up vector, well, it's really just that scaling factor times whatever the length of the original vector was, with the one caveat of that scaling factor, if it's not positive, well, we ought to make it positive, right? And so the best way to do that maybe is with these absolute values. So let's go ahead and show the proof of this, and I'll just kind of walk through it here. So the proof of this is actually just to do the computation. So if you want, again, we're trying to explore, right, what is the length of a scalar multiplied vector, right? So we have some scalar multiple c, we're multiplying it by some vector a, and so the first thing is, well, we know what scalar multiplication looks like, so we can go ahead and distribute the c to each piece. Then we could go ahead and take the magnitude of this vector, right? So that's where we go ahead and we square each component, sum them together, and throw them under the square root, right? That was the definition for the magnitude of a vector that we brought up in our last video. And now we can see that all of these things here have c squareds, right? Every single term here has a c squared, so I could factor that all out. And then there's a great property of square roots, or really all exponents, right, is that you can distribute it to each piece. So I could go ahead and take the square root of just c squared, and then I could take the square root of just this piece and multiply those together. And so you can see kind of all this stuff stays the same, but then the square root of c squared, remember this is a bit where it doesn't exactly cancel, right? The square root only gives out positives. So for instance, if you were to just take this really quick and say if c was -2, right? -2, square that, you'd get out 4, and then if you did the square root of 4, you don't get -2, you actually get +2, right? So it's not just c, but it's the absolute value of c. All right, so, and that's what gives us our final result here is, again, it's just the scalar multiple times whatever the length of that vector was, the magnitude of a, with a one caveat is if that scalar is negative, really ought to be positive, right? And so we use the absolute values to kind of fix the situation there. All right, last idea for the video is that we're going to talk about unit vectors, right? This is another property, right? When we're talking about magnitudes or length of the vectors, there are some vectors that we really like. I guess there's lots of vectors that I suppose we like, but one of them, or some of them are called unit vectors. So a vector A is called a unit vector if it has length 1. So length 1 vectors are quite nice. Really, it's just telling you all about the direction, and right, we've kind of, to some extent, have normalized the magnitude. So I'd like to show you how we can find unit vectors, maybe in a specified direction. So that's what we're going to be doing here. Here's an example. Find a unit vector in the same direction as this vector, 1, 2, 3. And so my first question is, well, is it already a unit vector, right? How far away are we? Maybe if it already has length 1, then my job's done, right? And I can just walk away. That's probably not the case, but let's see where we stand. So I'm going to go ahead and figure out what is the length of the vector right now, right? What is the magnitude? What is the length of this vector? And so again, based on our definition for calculating out the length, right, we're going to go ahead and take each piece, each component, we're going to square it, and we're going to add those components together here. Throw them all under the square root. All right, so 1 squared, that's 1, 2 squared, 4, 3 squared, 9, and so we get the square root of 14 after all is said and done. So sadly, right, the square root of 14 isn't 1, right? So it doesn't have length 1, it has length root 14. And so now we want to use this calculation really to our advantage, right? We want to scale our vector here, so that way it has the correct length, right? Because again, scalar multiplication, it doesn't really change the direction of the vector so much. I mean, maybe we could make it go in the opposite direction if we scaled it by a negative number, right? But for the most part, it's going to be going in the same direction, and then we can just kind of use this to modify the length. So, well, if this thing has length root 14, I'm going to go ahead and propose we do this. We're going to do 1 divided by root 14. And we're going to do this scalar multiplication with the original vector, 1, 2, 3. And I think this vector right here, right, first of all, it's in the same direction, but I think that this one has the correct length. So let's go ahead and check really quick. So if I was to ask, what is the length of this vector right here? Well, according to our theorem, up here, right, if you want to know what is the length of some vector multiplied by a scalar, well then really you just take the absolute value of our scalar. Well, the absolute value of a positive number is just that nice positive number. And then you multiply by the magnitude of the vector. And right, we already found that to be root 14. So this thing right here, this magnitude of this vector up here is going to be 1 divided by root 14 times root 14. So this thing would have length 1. So this thing, it's going in the same direction, right? Because again, scalar multiplication really doesn't change direction unless you multiply by a negative scalar, then it's going the opposite direction, fine, right? But otherwise, if you're doing a positive scalar, it's going in the same direction, right? And we've just shown that it has length 1. So this nice kind of multiplying by this reciprocal, this 1 divided by whatever its length is, this is a great way to make a vector, right, a unit vector, to make it have length 1. All right, so I'll have, in fact, maybe we'll skip this one really quick, and we're going to put this result in a box down here. So suppose that we have some vector, this is let me really denote this. I think I forgot to bold it there. All right, so this is a vector that is not equal to the 0 vector. Then, if you take that vector and you divide by its magnitude, right? So in this last case, we found that the magnitude was root 14. And so if we divide it by root 14, then this is a unit vector in the same direction that we started with. So the same direction as the vector A. All right, so that's a nice theorem. This is a good way to make vectors into unit vectors, is that you just divide by their magnitude. And the last little bit right here, find a vector of length 3 in the direction opposite of A. So this is kind of expanding on this even more, right? So now we don't want just a unit vector. We would like a vector of length 3, and we're not going in the same direction, but we actually want to go in the opposite direction. But kind of the steps are going to be very similar. We're going to start off by asking, well, maybe our vector's already length 3. That would be nice. We want to know what is the length of our vector as it sits. So we're going to go ahead and figure out what is the length of the vector right now. So I'm going to go ahead and do the square root of, so I'm going to just do the calculations here in this first bit here. So negative 2 squared, that would be 4. 4 squared, that would be 16. 1 squared, that would be 1. We add those all together, throw them all under a square root, and this gives us the square root of 21. So our length right now is root 21. So if I wanted to make this into a unit vector, I would go ahead and divide by this root 21, and I'd use that to multiply with my a. So a couple things here, right? I really don't want it to go in the same direction. I'd like it to go in the opposite direction. And so if I want to go in the opposite direction, then maybe you don't want to make this positive, but you actually want to make it negative. So that's the first thing. Now I'm heading in the direction opposite of A. So I've taken that into account. And then the last bit that I need to take into account is that I would like it to be not length 1. I don't want it to be a unit vector, but I want it to be length 3. So you can pause the video if you'd like and kind of think about, okay, how can I make this length 3? And then I'll spoil the surprise here, 2 seconds. So pause it if you'd like, and then we'll go over the result. All right, here it is. The answer is, instead of a 1 here, make this a 3. Right? And then we can go ahead and check. If you go ahead and ask, well, what is the length of this vector right here? Well, first of all, it's already going in the opposite direction. We see that with a negative. If you check and, again, apply this nice theorem that we have, well, you need to take the absolute value of this. So that would be positive 3 divided by root 21. And then the magnitude of this piece right here is this root 21. And so when you multiply these together, these perfectly cancel out, and this thing has length 3. So this right here would be a vector that's heading in the opposite direction of our original vector, right? Because again, we have this negative sign there. And instead of having length 1, instead of it being a unit vector, it has length 3. So this is how we can even expand on this theorem here and kind of really, we can make vectors any length that we want. And we can go either in the same direction as a specified vector or maybe the opposite direction. All right, so that's really the last big thing here. I have one page just to kind of say that all of the things, all of the properties of addition that you know and love back from adding numbers, these things apply with vector addition. And likewise, if you start to combine scalar multiplication here. So let's just maybe skim over a few of these really quick, right? You can add in any order. That's called the commutative property of addition, right? There's an additive identity, right? When you add 0, it doesn't change the vector at all. If you do scalar multiplication with 0, right, you get out 0. Let's see, you can kind of multiply in any order that you want. So this is the associative property of multiplication. Or of scalar multiplication here. There's distributive properties. This is the associative property of vector addition, right? So basically an add in any order that you can want. You can either add A plus B first or B plus C first, right? So if you want to add lots of things together, the order doesn't really matter. If you add A with negative A, you get back to 0. If you multiply by 1, you get itself, right? And again, kind of a distributive property with vector addition and scalar multiplication here. So, yes, everything that you kind of know and love from multiplication and addition of regular old numbers, real numbers, right, also apply here to vector addition and scalar multiplication. And the last bit here is that, especially maybe in physics or so, and I've seen entire textbooks who purely use this method. I want to make sure to bring up, there's kind of another standard way to write down vectors, and so I just kind of want to bring this up really quick here. These are called, well, we're going to use what's known as standard base vectors, and they are I, J, and K. So this is not the imaginary unit I, but this is now a new thing here, I, and this is the vector 1, 0, 0. We also have J, which is 0, 1, 0, and we also have k. So I, j, and k, these are the standard base vectors. You can kind of see there's one of each for kind of each core direction, kind of the first component, the second component, and the third component here. And notice that they're all unit vectors, right? If you were to take the magnitude of any of these things, that they are unit vectors. And so if you'd like to write your standard vector here, right, and here you have A1, A2, A3. This is one way to denote the vector. You can write it in the standard base form, and you would just write, well, whatever that first component is, that's along with the I. Whatever the second component, that's along with a j, and the third component, that's along with a k. And so instead of saying the first component, the second component, and the third component, it's probably better to say the I component, the j component, and the k component. Right, so this is another kind of standard way to talk about vectors. And so we'll just get a little bit of practice here. One last thing, if you want to pause the video and try this out, right, can you write these vectors right here as this linear combination of the standard unit vectors or the standard base vectors? So go ahead, try that, and I'll spoil the surprise here in 2 seconds. All right, the answer here is 5i plus 2j minus 4k. That would be the first one here. So that's how I'd write it in the standard unit vectors, the standard base vectors. And then for the second one here, if you want to write b, right, well, there's 0 i's, so in fact you don't even have to write that bit. You could say just pi j's and plus 100 k's. So that's how you could go ahead and write b with the ijk notation, or the linear combination of standard base vectors. All right, thank you very much, guys, for joining me. I hope you have a wonderful day, and I will see you out there.